Hopefully it works. For every unit, there's like a breakdown of things that you were supposed to learn. This is actually from our like teacher stuff. So you don't need to really overly stress about it. If you read it, you don't understand what it means. It's just like all the different things we've learned. I'm honestly just going to jump down to all the questions and work through questions. Okay, guys, we got to stop talking. So we'll basically just do questions and work our way through questions. Before we get into questions, it's probably a good idea to remember some of your mother functions, right? Like I call them like the original functions. So the very basic ones. Your log graph looks like this. Important parts of the log graph is where the asymptote is. There's a vertical asymptote right there at x equals 0. Exponential growth function is when your b value is greater than 1. It's a curve that will go upwards. The asymptote on that thing is right here. It's at the y-axis. That is y equals 0. And exponential decay is like an exponential growth, but flipped the other way. So it's a decreasing function, meaning it curves and goes down. It also has an asymptote at y equals 0. If you remember, once we got into transformations, we saw a lot of log things or exponential things being transformed. And a lot of the time they talked about where did the asymptote go? And then that was their way of getting you to think about transformations and how this graph is moved. Because transformations move your asymptote. All right, let's try some questions. Question number 1. The equation of the asymptote. There you go. The equation of the asymptote for the graph y equals log b x minus 3 plus 2, where b is greater than 0 and b cannot equal 1 is. Okie dokie. We're talking about the equation of the asymptote. We're talking about a log function. It's important to think about where the original log graph would be and where the original asymptote would be, right, on those mother functions. So a log graph would normally look like this, with an asymptote right there. That asymptote is at x equals 0. That would be a plain, boring log of x graph. We don't have that. We have log base b, x minus 3 plus 2. These things cause transformations to our graph. Right? It's moving it up, down, left, right, doing something to your graph. The values that are directly attached to the x are the things that move the x values, right? So left, right, and stretching left, right. The ones that are not attached to the x are changing your y value, so up, down, or stretching up, down. So for instance, like this 3 is directly attached to our x, so it is doing something to my x values. What is it doing to those x values? What's it doing to my graph? The purple. Horizontal translation, 3 units. Right. The blue one is doing something to my y values, right? So it's either moving up, down, or stretching up, down. What's it doing to my y values? 2 units up. So my graph would now look like this. It's gone to the right, and it's up a bit. That means the asymptote also moved to the right. And then the amount that it moved to the right was 3. So that asymptote is now at x equals 3. The answer would be C. Now, I know if that was a test question, a lot of people would just graph it. Right? Why wouldn't you graph it? Because you could look at it and be like, oh, where's the asymptote? And you could probably figure it out. The diploma and a lot of our unit tests and a lot of questions we've done tend to not use numbers and instead use letters. So if I saw something like this, like that equation has gone m to the right and n up. So that means my asymptote would be at x equals m because it's gone to the right. So just remember, you could do the same thing with letters, and you're having the same effect, right? You should think it through the same way. Try not to rely on graphing. If you rely on graphing, they do a good job of making questions that you can't graph, or at least can't easily graph. Number 2. The graph of y equals log x is transformed into the graph y minus 4 equals log x plus 5 by a translation of 5 units blank and 4 units blank. The statement above is completed by the information in row. Okay, looking at your equation, we have y minus 4 equals log x plus 5. That's not typically how we write equations. We typically write equations as y equals. That is not y equals. That's y minus 4 equals. So we're going to fix that. We're going to fix it by adding that 4 to the other side. And that's just going to help us kind of look at something more familiar, like what we're used to. And then from there, decide on the transformations. You don't have to do that step. But I find that it helps when we have something consistent, which is just y equals. The transformations would be 5 units left, right, because it's plus 5, and 4 units up, because that is a plus 4. Our answer would be B. Bueno. This one, 3. The graph of blah, 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 where 1 is less than B, the domain is. So that is a question where you could definitely go ahead and just graph it and check the domain. Like, that is a legitimate strategy there. Or you could try to use transformations to help you figure it out as well.
If you were going to graph it, do you just put a value in?
If you did want to graph it, just put a b value that follows that rule. So for instance, like b equals 2 would follow that rule. If I'm graphing things, I try to avoid using the number 1 or the number 0, just because sometimes 1 and 0 screw things up. So if it says b is greater than 1, I'm pretty much safe. Pick anything bigger than 1, and you could graph it. Or you could use transformations to do this. Let's start with transformations because that's what's intended. And then let's look at our graphing calculator, so at least we graphed at least one of these things. Perfect. Mother function of a log looks like this, with an asymptote right there. The domain of that function is currently x is greater than 0. Right? Domain is possible x values. It's not possible to have a negative x value. It's also not possible to equal 0, because that's what the asymptote is. So our domain is currently x is bigger than 0. If we transform this, that transformation is not 12 units to the left. Remember that we need to factor this so that the horizontal stretch is outside, and then I can actually identify my translations. So that thing is a stretch of 1/3 and then 4 units left. My new sketch would look like this: 4 units to the left. The stretch will not affect my domain. The reason it doesn't affect my domain is because the domain currently is affected by the asymptote, which is at 0, and 0 times any stretch is still 0. So only the transformation affected it. My new domain would be x is greater than -4. Answer would be A. Perfect. We'll graph this now on a graphing calculator so you can see what I mean by graphing things. You won't be able to see this in the video, so I'll pause the video. Hopefully it does. Yeah. All right, number 4. A student sketched the graphs of f of x equals log a x plus 3 minus 7, and g of x equals a to the power of x minus 2 plus 5, where a is greater than 1, on a coordinate plane. She also drew the asymptote of the two graphs using dotted lines. The intersection points of the two dotted lines will be at. Ooh, tricky. So, they graphed two functions. This one and this one. We should also graph those things. If you graph them, just sketch them quickly by hand. The first one, the red one, is a log graph. So it's going to be our one that goes up and over. We've done it like 5 times now. It's going to be 3 units to the left, 7 units up. It'll look somewhat, down.
I was so confused there.
It'll look like this. The asymptote of that will be here. The asymptote is at x equals -3.
You don't even need it anymore.
Pardon?
You don't even need it.
That's all you need.
Literally, you can answer the question like
That's all
that.
you need.
Yeah, those are some bad options for trick answers. Let's do the blue one. So a regular exponential growth function. I know this is growth because a is bigger than 1. Our regular growth function, we haven't done yet, looks like this. This is not a regular growth function. This function has gone 2 units to the right, 5 units up. So it now looks like this. And it has an asymptote that's horizontal. It's normally an asymptote at y equals 0. But because I move this graph up 5, that is now y equals 5. They said that she drew the asymptotes with dotted lines. The intersection point of the dotted lines, that means the intersection point of the asymptote, is right here. That point is -3, 5. Again, if they replace all those numbers with letters, so say they put M and N, right? My asymptote would now be at M, -M. This asymptote would be at whatever that letter was. Say it was L, right? It's gone up L. So you could do that with just generic letters as well and not have to use numbers. Cool. Question 5. The y-intercept on the graph f of x equals a, x to the power 1, x plus 1 plus b is y-intercept. To calculate a y-intercept is a throwback to math 10. What do we know about all y-intercepts? X equals 0. Perfect. They told you x equals 0. Figure out what y will equal. So for us, This is y. So I have y equals a to the power of 0 plus 1 plus b. A to the power of 0 plus 1 is a to the power of 1. Right? Because 0 plus 1 is 1. A to the power of 1 plus b. My y-intercept is a plus b.
Crazy. We've never got that.
Not bad. As long as you remember that y-intercept means x equals 0.
We just solved.
And then just, reduce it, right? Because there is no values for a and b. So you're just reducing it. Recycle. All right, let's look at number 6.
Here too was good.
That's what I said.
The graph of y equals 3 to the power x is reflected in the line y equals x. The equation of the transform graph is, this thing, reflected in this. Visually, what they've done, if they had given you a picture, which they didn't, but visually what they've done is they have taken your graph and they've reflected it over that line. That perfect diagonal line is y equals x. So anything that was on this side of the line would be flipped over here. Anything that was on this side of the line would be flipped there. That's visually what's happened. We don't have a visual representation, so it's not actually going to be useful to us. But just like knowing what they've done is good. Mathematically, when they reflect over the line y equals x, what have they done? It is an inverse function. Meaning they've taken x and they've changed it with y. So my new function is x equals 3 to the power of y. Right? They took x and y and they switched them. You'll notice that answer is not there. So x equals 3 to the power y is true. That is the inverse. That is none of our solutions. All of our solutions are y equals. Y equals, y equals, y equals, y equals. So we need to change ours to be y equals. When something is in the exponent and you're hoping to get that thing by itself, that's exactly why logs exist. It's the whole purpose of a log. We can take, I'll do this with random letters. Let's do y equals, no, different letters. I don't want to use y. Let's do a equals b to the power of c. I could convert that into a log by saying log base b, because that's the base of the power. The argument becomes whatever was isolated before, and that will equal the exponent c. That is how you change a power into a log. You use that so you can get exponents by themselves. There's no other way to isolate an exponent. You have to do it that way. In this case, I'm trying to isolate y. So I need to change this into a log. So I go log the base of the power becomes the base of the log. So this will be base 3. Whatever was isolated becomes your argument, and your exponent becomes isolated. My answer is log base 3 of x is equal to y. You obviously could flip those sides. That means y equals log base 3 of x. That is a. Y equals log base 3 of x. That requires you to identify what it means to reflect, so it means inverse, and it requires you to be able to change it to a log. Number 7. A function y equals, I don't know why I just had like a total brain fart there. A function y equals, why do I still not like that? It's like breaking my brain. Y equals a times 2 to the power of bx passes through the points 3 comma negative 6 and 6 comma negative 12. What is the value of a? Okay, looking at this guy. I have 4 unknown things there. I have y, a, b, and x. If they're asking me to solve for one of those letters, which is what they're doing, that means I must know the other 3 somehow, right? They said find a. So I need to be able to figure out what y, b, and x are. Unfortunately, they never tell you what b is. All they give you is these 2 points. These points are x and y values. The reason they give you 2 points is because you have 2 things you don't know, a and b. That means you need to make 2 equations using those 2 points so you can solve the 2 unknown things. Equation 1 is when you use x equals 3 and y equals negative 6. So equation 1 would be y, I'm a liar, it'd be negative 6 equals a 2 to the power of b times 3. That's your first equation using your first point. Your second equation is when x equals 6, y equals negative 12. That would be negative 12 equals a 2 to the power of b times 6. I now have 2 equations, 2 unknowns, a and b. That's why they gave you 2 points. Perfect. To solve that, you need to do one of 2 things. You could do substitution or elimination. It's like a systems of equations, right? So you need to either use substitution, which means figure out what one of the letters is, substitute it into the other one. Or you can do elimination, which means you make both things kind of the same somehow, and then subtract or add them together. There is kind of like a third strategy we could use. Because we could graph it in a messy way. No, I don't think I like that though. No, we're not going to graph it. That's just too messy. What I would do is I would look at that and I would notice that these things are very, very, very similar. The one on the left is equal to negative 6. The one on the right is equal to negative 12. So if I could make them the same, then it's probably easy to work with. And then I actually could graph. Do I want to graph? Maybe their best bet. So we're going to use substitution. You could, I just hate graphing. Yeah, let's do substitution. So you want to get one of the letters by itself. It doesn't matter which letter you choose. Okay, you just have to get that letter by itself. Let's work with the one on the left. I'm going to clean it up a little bit. So instead of writing it as B3, because I just think that looks bad, I'm going to rewrite it as 3B. It just looks cleaner, right? I'm getting rid of my brackets. Perfect. You have to get one of the letters by itself. Doesn't matter which one. It's probably easiest to get A by itself. So let's get A by itself. To get A by itself, I have to divide 2 to the power of 3B to the other side. And it doesn't look pretty, but it should work. We have negative 6 divided by 2 to the power of 3B is equal to A. This means I can substitute this fraction for a in the other equation. So I take it and I substitute it over here. And I now have negative 12 equals that ugly fraction, negative 6 over 2 to the power 3b times 2 to the power of, instead of b bracket 6, I'm going to fix that a little bit, 6b. I hate 6's and b's being next to each other.
Yeah, I can see that.
Right? They look the same. Perfect. From there, it's not nearly as bad as it looks. Like, it looks about as terrible as you could get for a math equation, but it's not that bad. The reason it's not that bad is because when I multiply things, you just multiply to the numerator, right? So I can clean this up and write it like this. Negative 12 equals negative 6 times 2 to the power of 6b divided by 2 to the power of 3b. Right, like a fraction times something, you just multiply the numerators together. And now hopefully you see it's not that messy because I have two powers that are the same base. I have 2 on the top and I have 2 on the bottom. That means I can use my exponent laws and I can subtract those exponents from each other. 6b minus 3b is 3b. So this is negative 12 equals negative 6 times 2 to the power of 3b. I use my exponent laws. 6b minus 3b would be 3. My goal here is to figure out what b equals.
Isn't it divided by 2?
Because it's the same base they go up.
Yeah, the base will go up because it's like combining them together. Like if I had, let's like simplify it. If I had something like this, that would equal x to the power of 2, right?
Yeah.
Not x to the power of 2 divided by x. By putting an x on the bottom, you'd be saying that there's still 1 there. And then you'd use your subtraction rule again. So if I was dividing by 2 still, then I'd have to use my exponent law again. Right, like,
Okay. I don't know.
we'll blame it on English.
Yeah.
Think about, so if you looked at this again, exponent means you have a certain number of things, right? So this is saying that you have 4 x's. Only a couple of them are crazy. On the bottom, you have 2 x's, right?
Yeah.
That's a funny x joke. You guys suck. Right? These cancel, and I'm left with x squared. But there's no x's on the bottom anymore. That's essentially the same thing I've done down here. The exponent laws. So I don't know how many 2's I have, but let's say b equals 1. If b was 1, that means I have 6 2's on the top, right?
Yeah.
And 3 on the bottom.
Yeah.
So that would go cancel, cancel, cancel. And I have 3 left on the top, but none on the bottom. So I wouldn't have a divide by 2 anymore.
Okay. I now understand.
Even if you don't, I appreciate you being like, like, please stop. Leave me alone. It's weird when you do rules with letters, right? Like that, it's a trippy concept. See if I can erase all this. Okay. Solving this thing. So I'm trying to figure out what b is here. Right? B is in the exponent. So to figure out what b is, I'm going to have to get b by itself. That means I'm going to have to change it into a log. I can't change that into a log. The reason I can't change that into a log is because the power is not by itself. You have to divide the -6 to the other side first. Otherwise, that -6 would have nowhere to go in our conversion into a log. So I divide by -6. I now get +2 equals 2 to the power of 3b. From there, you might even just be able to figure out what b is. If not, that's fine. We need to convert that into a log. So this would be log base b, base 2. The argument is whatever was by itself equals 3b. So that's me taking a power, changing it into a log. Log base 2 of 2 is actually a log law. So if you have the same base and the same argument, which we have here, same base, same argument, that means the entire log equals 1. Same base, same argument, that log equals 1. So I actually have 1 equals 3b. Divided by 3. I get 1 over 3 equals b.
Could you just solve the log? Because it gives you the same
Yep.
thing.
If you go log base 2 of 2, it equals 1. The problem is if that was, say, like log base y of y. Can't calculate that, right? So identifying like same base, same argument equals 1 is a good idea to know. The question, I don't think asked for b, did it? It asked for a. What is the value of a? The good thing is once you know one, the other one's usually not hard. So I go back to this equation here. And I realize a is equal to -6 divided by 2 to the power of 3 times b. And I can just change b to be 1/3. So it becomes -6 over 2 to the power of 3 times 1/3 equals a. 3 times 1/3 is 1, so this is -6 divided by 2. It's -3 equals a.
Silly question. You can't go back to that formula that you just used in the range.
Pardon?
You can't go back to the formula you just used to find that 1/3.
You could, to a certain point. I could put it back into this.
Yeah, that's what I mean.
Yeah, and that way it would work, but it would just be, it wouldn't be that messy actually. You could. Because this one's going to be the easiest one.
Yeah.
All right. Log laws. Our friend the log laws. I think if we remember correctly way back in February, right? February. And then you remember how to spell it properly. February. If we go back to Feb, that's better. We could remember that log laws kicked our butt a little bit. I think we did that first quiz. We did okay on the calculating, the converting. That stuff was all right, but the log laws was a struggle for us. And then we studied and practiced it. We did our test and it still kicked your butt. And then I moved on and said, tough luck. So it's probably something you should spend some time on if you remember back then that was hard for you. It's usually because it doesn't say use log laws. You just have to know to use log laws, which is a tricky skill. And if you look at this, at no point does it say use log laws. It just says the expression this is equivalent to, and somehow all those crazy logs turn into a nice number, which seems insane. Okay? So somehow we have to use log laws here. Your log laws are on your formula sheet. I believe if you look on the left side of your formula sheet, you'll see log laws are there. For log laws to work, you have to have the same base. So if I look, recognizing that these are both log A, that's a hint I should use log laws. I'm gonna be like, something's going on here. They're the same base. Why are they the same base? Our first log law we're gonna look at is what happens when you subtract logs. When you subtract logs, you take the arguments of the logs and you divide them. So the first log goes on the top, A4B, and the second log goes on the bottom. And our hope here, by combining these logs, is that somehow we can simplify and reduce these things. Lucky for us, we can. So when we combined those logs together, we got a fraction in the argument. We can use our exponent laws here. I have a to the power of 4 divided by a to the power of 1. That'll become a to the power of 3. And I have b to the power of 1 divided by b to the power of 1. Those will cancel out. And I now have log base a of a to the power of 3. Cool. None of our answers match up with that. The next thing that I notice that's kind of suspicious to me is that I have a in my argument and I have a in my base. And I remember the log rule that I just talked about, last question, that's why I remember it, which is if you have the same base and the same argument, that's going to equal 1. But that is not same base and same argument because of the power of 3. Right? So I can't turn all that into 1. I have to get rid of that 3 somehow. To get rid of that 3, I use a different log law that says exponents can be rewritten as coefficients. So I rewrite this as 3 times log a of a. And now I can use my handy law, same base, same argument, this whole thing equals 1. That means it's 3 times 1, which is just 3. Answer's A. Crazy. For the record, that's not the only way to use log laws to solve that question. So if you saw another strategy or did another strategy, then you may have got it right and done something completely different. I feel that's the most efficient strategy through. Next on the docket. Number 2. Log r divided by t plus log d divided by t is equal to. Okie dokie. First things first. I notice there's no base on those logs. If there's no base on a log, what does that mean? 10. Perfect. So that's not going to make a difference here. But that would have been one of the first things I did notice. Was like, hey, there's no base here. This means log base 10 of r, log base 10 of t. Cool. Next thing I do is I look at that and I notice that I have adding. And there is a log law for adding. The log law for adding is that I get to multiply the arguments together. Now, this has common denominators, which is nice. If it didn't have a common denominator, you'd have to get a common denominator, right? Just so you can combine those fractions. That would be a lot meaner, but isn't unrealistic to expect from you to be able to get a common denominator, right? So this thing really is log r plus log d over t. Get a common denominator, combine the fractions. Then use my log law of adding. My log law of adding is you multiply the arguments. So this becomes log r times d divided by t. I suspect most people would get there. And then maybe cry, like just a couple tears, not a lot, because it doesn't match up with any of the answers. And then you'd be like, what am I doing? Some of those answers have square roots, some of them have exponent t's. Like, it looks like an absolute mess getting from where we are to where they are. And it really comes down to two tricks. The first one has to do with coefficients. So we actually have a coefficient here. I can rewrite fractions. Instead of saying divide by t, I could say 1 over t times log of RD. That's equivalent. And the reason that's so important to us is because coefficients in logs can become exponents. But in this moment, it doesn't really look like a coefficient, does it? It looks like you have a log divided by something. So recognizing that division can be rewritten as a coefficient is the trick that I think is the hardest there. Once I have a coefficient, I can take said coefficient and write it as an exponent. So this becomes log R d to the power of 1 over t. Which still is not one of our answers. That's why I said there was two tricks we had to know. The second trick we have to know is that fraction exponents make radicals. The bottom value of the fraction is your index. The index is the bottom. Some little dance, something about Shabby with a dance. So this becomes log root bottom of the fraction becomes the index of the root. Everything else, so RD to the power of 1, is your radicand. Is log t root of RD, which is C. That would not be a standard of excellence. A standard of excellence is typically if they take two full concepts and blend those two concepts together. So for instance, on your perms and coms test, mixing polynomial functions with perms and coms. People shaking their heads all over the place. That is a standard of excellence type question. Oh, sorry. Thank you. I just saw routine got excited. Yeah, it is B. It's definitely multiplication.
Yeah, and I was like, when did we start adding them? Yeah. Honestly, I like these guys.
Yeah. So when we do, I'm trying to think if any of these have been standard of excellence yet. Maybe number 4, because that's doing transformations mixed in with the asymptotes of log functions. But that would be, I don't even know if that would count as standard of excellence. Typically, they put transformations into everything. Okay, number 3. Given that log 2 of z equals 9 and log 2 of w equals 5, determine the value of log 2, 16 root zw. Different ways to tackle this.
So the W is not.
Pardon?
The W is just not.
The w is not underneath that root sign. That w is by itself. So it's root z times w right here. Those are not both underneath roots. Different ways to tackle this. For me, when they start saying this, they say given, and then they give you a bunch of info like that. My job is to use that info to simplify this thing. Like use it to mess around with this. So if I can somehow get this to become like log 2z or log 2w, then I can start changing this into just numbers like 9 and 5. So this is again a log question. But instead of using log laws to combine things, we're going to use log laws to break apart something. This can be broken apart. The reason it can be broken apart is because there is multiplication in between those 16 and root z, and there is more multiplication in between the root z and w. So I could rewrite this as log 2 of 16 plus log 2 of root z plus log 2 of w. And like I can break it all apart.
Wait, with the first information, can't you just figure out what your z and your w is?
You could. So you could take that first one, redo it into a power to figure out what z equals, and you could do the second one, you could redo it to figure out what w equals, and you could substitute those values in. And that would work perfectly fine. For me, I took this thing and split it apart, and then I can start to calculate. So log 2 of 16, you put that in your calculator. The answer is 2, 4, 8, 16. The answer is 4. I count with my hands. Plus, I don't know what log 2 root z is. I know what log 2 of z is. So I rewrite that as log 2 of z to the power of 1/2. Again, using my trick that radicals can become fraction exponents. Plus, log 2 of w, they told me was 5. So I have 4 plus log 2 of z to the power 1/2 plus 5. Now I can do log 2z equals 9. So this is 4 plus 9 to the power 1/2 plus 5. You throw that thing in your calculator and you get an answer of 12. Amelia's suggestion was to take these things and solve them for z and for w, which works beautifully too. So log 2z of 9 can be rewritten to be z equals 2 to the power of 9. This one can be rewritten as w equals 2 to the power of 5. 2 to the power of 9 is the big number. 512?
I ended up getting 13.5.
That's why I'm good as well.
What?
I got 13.5.
Hold up. Why? 2, 4, 8, 16, 30. This is 32, right? Okay. Did I make a mistake? There's a good chance. Oh, yeah, I did make a mistake. I forgot to move this exponent is a coefficient. Good thing you guys calculated it. Meaning that's not 9 to the power of 1/2. That's 1/2 times 9. That's better. That will give you an answer of 13.5. That's better. That's what you got, right? 13.5? Yeah, okay. Yeah.
Can you just go look at this really quickly?
Yep.
What's going on?
That I can do.